Hello students, next lecture, active membrane potential. I have uploaded 2 lectures already. You have to go to the previous lectures and you have to go and see the previous lectures. You have to attend the lecture and then you will be able to understand this. This is the board of the last lecture. This is what we studied in the last period. Okay, let me just clear it off so that we can go on with the next topic that we're going to discuss. We are going to discuss the active membrane potential and the initiation of the active membrane potential, how the active membrane potential is going to be initiated. We have already studied about the resting membrane potential and the resting membrane potential, the conditions of the resting membrane potential. The resting membrane potential, as all of you know, it is due to a specific distribution of sodium and potassium ions across the axonal membrane. We will be going over the main points again. It is a distribution of ions across the axonal membrane, and the neuron in this situation is said to be in a polarized state. It is said to be in a polarized state. Now, what we are going to see is we are going to disturb the neuron, we are going to disturb the distribution of ions across the membrane. And the neuron is going to be in a depolarized state. Now, how is the distribution going to be disturbed? The distribution is going to be disturbed by a stimulus. And this stimulus, it has to be adequate. Adequate means it has to be enough to carry out the change. It has to be enough to bring about a change in the ionic distribution. It has to be enough to bring about a change in the ionic distribution. And such a stimulus is said to be an adequate stimulus, right? It is said to be an adequate stimulus. Now, what we are going to see is what is an adequate stimulus. An adequate stimulus is also known as the adequate threshold. It is known as the threshold stimulus. It is said to be a threshold stimulus. And if the threshold is not enough, then it is called a subthreshold. I have already discussed this in the previous lecture, in which we studied about the RMP. Today, we are going to study about the active membrane potential, AMP. We are going to study about the active membrane potential and what is the basic characteristic of the active membrane potential. The basic characteristic of the active membrane potential is a more positive inside as compared to outside. More positive inside, right? It is going to be a more positive inside. What? A more positive charge inside as compared to outside. And outside, what are we going to have? We are going to have a more negative charge outside. This is the case in which the disturbance of charges, the disturbance or distribution of what? Distribution of sodium, distribution of potassium, disturbance of the working of the pumps and the channels has taken place. And who has disturbed them? It is the adequate threshold. It is the adequate stimulus that has disturbed them. Now, in this condition, our neuron is said to be in a disturbed state. It is said to be in the active membrane potential. There are various steps involved in the distribution, in the disturbance of the neuron. When the neuron is stimulated by any kind of external or internal stimulus, the first step is going to be the disturbance of the ionic distribution, ionic distribution across the membrane, disturbance of the, when a neuron fiber, number one, now we can write it down stepwise. When a neuron fiber is stimulated by a stimulus of adequate threshold, now this is going to be the first point. It is going to be the first point, and that is disturbance by an adequate stimulation. This is the first point. Then what happens? When the neuron is going to be disturbed by an adequate stimulus, the area of the neuron, the area of the fiber that is receiving that stimulus that has been disturbed, a change occurs in it. And what changes that? It becomes very highly permeable. The permeability increase. Permeability to what? Permeability to the sodium ions. The permeability to sodium ions, it starts to increase. And it starts to allow more sodium to move inside. Now the permeability to sodium has increased. Number one, stimulation. Next, that point is going to be the permeability to sodium is going to be very, very highly increased as compared to potassium. Potassium permeability will not be increased. Now, number three, what is going to be the next change after the permeability has increased? What happens and why is the permeability increasing? The permeability is increasing because of the opening of the sodium gates. Sodium gates are going to be open. And because of the sodium gates opening, what is going to happen? Number four, when the sodium gates are opening, now more sodium is going to move in. More sodium will move in. And when more sodium is going to move in, then what happens? The concentration of sodium is going to be more inside the exon cytoplasm. It is going to be more inside the exon cytoplasm. So this is going to be number 5. Increase in the sodium ion concentration in the exoplasm. Increase in the sodium ion concentration inside the exoplasm. Why? Because of more movement of the sodium. Now, as the sodium has started to enter more, now what is going to happen? The next point is going to be a change in the charge, a change in the voltage, which is minus 70 millivolts. It is now going to be towards, it is going to go towards minus 70, is going to go towards 0. That is, it is going to be neutralized. And then from 0, it is going to move to 50 millivolts. Means now it doesn't have a negative charge. It means that a reversal of charges has taken place. And now this is what is happening when the threshold has been applied. Reversal of charges has taken place. This reversal of charges that has taken place, a change in this reversal of charges that has taken place is known, is giving us a situation which is known as depolarization. It is called depolarization. Number 7 point is the reversal of charges, which is called depolarization. This electropositive inside and electropositive outside, it doesn't last for a very long time, but it lasts for only 1 millisecond, about only 1 millisecond. It just lasts for about only 1 millisecond. But in that 1 millisecond, what happens as a result of this depolarization? What happens that the sodium gates, it will continue to remain there until the sodium gates are not closed. After the sodium gates have opened and now the sodium has moved in and depolarization and disturbance has taken place. Now in this situation, now our neuron is said to be in a depolarized state, in a disturbed state. Now this is the area that the threshold was applied. This disturbance is going to move adjacently now. It is now called as the action potential. It is called the action potential. And this action potential is going to move forward adjacently. It is going to move forward to the surrounding areas in order to neutralize the surrounding areas. Once the action potential moves forward, the area that is left behind, it has to be repolarized. Now, this is the next step. Repolarization. First of all, depolarization, now repolarization. Once the action potential has moved forward, now repolarization, repolarization of the neuron, going to maintain the distribution. A fraction of a second after the sodium gates have opened due to the threshold, the depolarization of the axon membranes has taken place. And the depolarization of the axon membranes takes place at the 50 millivolts. It takes place at the 50 millivolts. Now, when this depolarization has taken place, what happens now? The potassium gates will start to open. The potassium gates will start to open when 50 millivolt has been achieved. The potassium gates will start to open. These potassium gates, they will start to open, and what will happen now? These potassium gates, they will allow potassium to move out of the cell. They will allow potassium to move out of the cell. That means now positive is going to start to move out. Positive is going to start to move out in the form of potassium. This potassium is going to move out, and the process to maintain the initial polarized state has started, and this process is said to be repolarization, right? As the potassium starts to move out, eventually what happens, the cell becomes less positive inside as compared to outside. Therefore, a negative and a positive charge is maintained again inside, and the neuron is said to be repolarized. But because uncontrolled movement of potassium has taken place, so the balance of repolarization, after repolarization, it is not as is required in the resting membrane potential. Resting membrane potential is 30:1 inside out potassium and 1:10 inside out sodium. This is the balance that is required, but during repolarization an imbalance has taken place. The balance has been disturbed. So, and then we have a lot of positive outside and as compared to inside. So therefore, there is a disturbance in the positive and the negative distribution across the membrane. The membrane is having a negative charge inside and positive outside. Okay, one condition has been settled, but the concentration of the ions, the distribution of the ions is not yet balanced. And for our neuron to behave normally, this distribution is very, very important. In this situation where we have a very high number of positive ions outside, our neuron is said to be in a hyperpolarized state. Our neuron is said to be in overpolarized. Our neuron has become overpolarized. Our neuron has become hyperpolarized. And this happens at the peak of the action potential. When the sodium gates, they close and sodium permeability declines, then what happens? The sodium potassium pump, it keeps on working, but in this situation, it is throwing out a lot of potassium outside. And the sodium gates, they have been closed. And due to this, at the spike of the action potential, the membrane, it becomes in an overshoot of negative charges inside as compared to outside. And this overshoot of negative charges inside as compared to outside is said to be hyperpolarization. And why? What is the cause of this hyperpolarization? It is due to the slight delay in closing of the potassium gates as compared to the sodium gates. And as the potassium continues to return to the it continues towards the outside, then what happens? Okay, we have a more positive outside as compared to, and there is an imbalance of the charges. And now our neuron is not in a polarized state, it is in an overpolarized state. The concentration has disturbed. We have a very high positive outside and a very high negative inside, which is a disturbed polarization. Our neuron will not be able to conduct anything in this state, because for the neuron to conduct a message, what is required is the specific ionic distribution, the specific ionic concentration across the membrane. The membrane potential has to be very, very specific. Right. To maintain this membrane potential, then this period in which our neuron is in a very high state of polarity is said to be in a hyperpolarized state. This is said to be the refractory period. It is said to be the refractory period. During this refractory period, what happens after an action potential has taken place? Be very, very careful. After an action potential has taken place, the nerve fiber, it undergoes a period of recovery. This is the period of recovery. It's known as the period of recovery, in which it is going to repolarize itself. Okay? This period of recovery is that in which the original ionic distribution and polarity has to be revived. It has to be redone again, and it has to get ready for the next stimulation. This recovery period of the nerve fiber is said to be the refractory period. After the hyperpolarized state, the neuron has to recover itself to the normal polarity. If not, it will not be able to send any kind of messages. And this period of recovery after hyperpolarization is said to be the refractory period. Now, the recovery period of the nerve fiber is called the refractory period. After an action potential, the nerve fiber undergoes a period of recovery in which it has to regain its original ionic distribution and polarity, and it has to prepare itself for the next stimulation. The part of the recovery period in which the nerve fiber is not able to give any response to any strength of threshold is said to be the absolute refractory period. Now, in the refractory period, we have another state which is called the absolute refractory period. It is said to be the absolute refractory period. During the refractory period, the nerve is not at all going to be able to transmit any kind of messages. Although a repolarized neuron has the same type of charge distribution, positive outside and negative inside, but the disturbed situation in this condition is that the potassium and sodium concentration is disturbed. We have a very high amount of potassium outside, which is in the normal state has to be present inside. So the repolarized nerve fiber, it has to undergo the refractory period of a few milliseconds, during which the original ionic distribution has to be restored. And how is it going to be restored? It is going to be restored by the sodium potassium exchange pump, which actively transport sodium ions and potassium ions in and out until the normal concentration has been maintained. Now, this was all about active transport. Let me go to the slide, let me go to the presentation, and then let us see what we have in the presentation. I hope you people, you can watch the lecture over and over again, because I know that it is not a very easy topic. I have tried to make it very easy for you people. Go over and watch the lecture again so that you can get the main concepts. In case you need more details, please do send me a message so that I can get your message and I can prepare a detailed lecture for those who require a more detailed lecture. The major factors involved in the active membrane potential are the sodium and potassium movement, the reversal of charges, the passage of the nerve impulse, and the membrane potential. Now, initiation of nerve impulse occurs when there is an entry of an appropriate stimulus, which is the threshold. Now, this is where the threshold has been applied, and this is the reversal of charges. This is the action potential. This action potential is going to move forward. It is going to move. And once the action potential moves forward, this is where repolarization is taking place and hyperpolarization occurs. And then the refractory period is going to come over. The action potential keeps on moving forward. It tries to neutralize the adjacent areas. It is going to move in a forward direction. It tries to neutralize the adjacent areas. And as it tries to neutralize the adjacent areas, this magnitude of action potential shifts forward across the neuron at a very, very high speed. The neuron can conduct up to 250 impulses per second. And neurons that are myelinated, they conduct impulses at a very, very high speed as compared to neurons that are non-myelinated. Resting membrane potential, a stimulus localized in the change of the resting membrane potential, that depolarization of the membrane. This is the depolarization of the membrane, a more inside becoming more positive than outside, and the action potential is established. The major factors in changing of RMP to AMP, movement of ions of sodium and potassium, nerve impulse, opening of the sodium gates, sodium moving into the neuron, making the inside more positive, reversal of charges, movement of ions causes the inside more positive as compared to outside. Voltage becomes from -70 to 0, from 0 to plus 50. Passage of nerve impulse takes place. The nerve impulse is conducted at a speed of 120 meters per second. Active membrane potential is going to be, this is not a negative sign. Please do not consider this negative sign. It was a typing error. Soon after the passage of the impulse, the resting membrane potential has to be restored back by the movement of ions. This is the refractive period and the hyperpolarization, where the hyperpolarization takes place. Myelinated neurons, they serve to transmit messages faster as compared to non-myelinated neurons. Messages jump across the myelinated neurons, and such messages are called the saltatory impulses, in which the message jumps from one node of Ramvier to the next node of Ramvier. The normal speed in the of nerve impulse in humans is about 100 meters per second. Action potential. This is the action potential in the local area of the plasma membrane. It is in the orange color. There is a reversal of charges over here. This action potential then causes the production of another potential in the adjacent area, and the action potential, it moves forward. It keeps on moving forward in this direction of the arrow, and at the back we have the repolarization stage taking place. In the next class now, what are we going to do? We will be studying about the synapse. Synapse is a very interesting topic that we will be studying in the next class. See you people next time. Take care of yourself, and I will be with you with synapse soon. Okay, goodbye. Allah Hafiz.